There are several combinations of e to the x and e to the negative x that come up quite frequently in application. The two most common ones are what we call the hyperbolic sine and the hyperbolic cosine. Now, just for short, I call the hyperbolic sine the shine and the hyperbolic cosine the cosine. So here's how they're defined. The shine is e to the x minus e to the negative x, all divided by 2. And the cosine is e to the x plus e to the minus x, all divided by 2. You can see that they're pretty similar in their definition. We can then define 4 more hyperbolic functions. We can make the hyperbolic tangent or thangent by taking the shine divided by the cosine. Of course, the cotangent would be the cosine divided by the shine, and the secant, hyperbolic secant in other words, would be 1 over the cosine, and the hyperbolic cosecant, the cosecant, would be equal to 1 over the hyperbolic sine, or 1 over the shine. So one application of this cosine, you see it every day if you see wires stretched between power poles. The wires tend to sag a little bit, and the shape of that sag is actually related to the hyperbolic cosine. So it's a cosine shape. Okay, so another property that they have that makes them kind of nice and gives them their name hyperbolic, if I were to make my location in the plane function of t by letting x be the cosine of t and y being the sine of t, so if I were just using these two functions to determine my x and y location, then x squared minus y squared would be e to the t plus e to the negative t over 2 squared minus e to the t minus e to the minus t all over 2 squared, which, if I FOIL this out, the denominator squared is 4. E to the t plus e to the minus t is e to the t times e to the t, that's e to the 2t. E to the t times e to the minus t is e to the 0, so that's 1. I get that twice when I FOIL this out, so I get plus 2 plus e to the negative 2t. That's just the cosine squared then, minus the sine squared is basically the same thing. You get e to the 2t and e to the negative 2t, but the middle term is negative 2. Oops, not a t, just negative 2 all over 4 here. If I combine these, I have e to the 2t minus e to the 2t, so those are going to cancel. I have e to the negative 2t minus e to the negative 2t, so those are going to cancel. And I have 2 minus minus 2, that makes 4. So I have 4 over 4, which is 1. So the equation x squared minus y squared equals 1 is the equation of a shape called a hyperbola. And that explains why these are called the hyperbolic sine and hyperbolic cosine, because they satisfy the equations of hyperbola. Unlike this situation, or somewhat similar to, I guess, if x was the cosine of t and y was the sine of t, then x squared plus y squared would be the cosine squared plus the sine squared, which we know is 1. So this is the equation of a circle, which is a special kind of ellipse. So the regular sine and cosine have to do with circles or ellipses. The hyperbolic sine and cosine have to do with hyperbolas. This is the identity that we've just shown here, that the cosine squared of a number minus the sine squared of that same number is equal to 1, right? As opposed to, for the elliptic ones, the cosine squared plus the sine squared is equal to 1. So similar but slightly different. Let's look at the derivatives of these hyperbolic functions. So first, let's take the derivative with respect to x of the hyperbolic sine, or the shine. We're talking about taking the derivative with respect to x of e to the x minus e to the minus x all over 2. which is easy to do because the derivative of e to the x is e to the x, and the derivative of negative e to the negative x is plus e to the negative x, because the derivative of e to the negative x is e to the negative x times the derivative of what's inside, which is negative 1. That negative multiplies that negative and gives us plus. Okay, which is actually the cosine. So the derivative of the sine is the cosine. That's just like the derivative of the sine is the cosine, huh? So, but the derivative of the cosine, now we're talking about the derivative with respect to x of e to the x plus e to the minus x all over 2, which would be e to the x, and then the derivative of e to the negative x would be e to the negative x times the derivative of what's inside, which is negative 1, so negative e to the negative x all over 2, which is the sine. So it's a little bit different because the derivative of the elliptic cosine, the regular cosine, is the minus sign, but the derivative of the hyperbolic cosine, the derivative of the cosine, is just the regular sine. Now, we can use those two facts to find the derivatives of the others. For example, if we need to find the derivative with respect to x of the tangent, we're really talking about taking the derivative of this quotient, the sine, over the cosine, and the quotient rule says you take the derivative of the top, and the derivative of the sine is the cosine, times the bottom, which is cosine, minus the top, which is sine, times the derivative of the bottom, and the derivative of the cosine is the sine, all over the bottom squared, so all over the cosine squared. But we just showed that cosine squared minus sine squared is 1, so we have 1 over cosine squared, and 1 over the cosine is the secant, so this is the secant squared. So the derivative of the tangent is the secant squared. Let's look at another one. Let's take the derivative with respect to x of the secant. We're really talking then about the derivative with respect to x of 1 over the cosine. I guess we could do that by the quotient rule. The derivative of the top is 0 times the bottom minus the top, which is 1, times the derivative of the bottom, which is the sine, all over the bottom squared. So we have basically then a negative sine over a cosine times a cosine, and sine over cosine, that's the tangent, so we have negative tangent, and 1 over cosine is the secant, so we have the negative tangent secant. So that's a little bit different than for the regular secant, right? The derivative of the secant is the positive secant tangent, so there's an extra negative sign. The reason is because the derivative of cosine isn't negative sine, it's positive sine. Let's do the other two. We need to find the derivative with respect to x of the cotangent, which would be taking the derivative with respect to x of the cosine over the sine. And according to the quotient rule, that's the derivative of the top, and the derivative of the cosine is the sine, times the bottom, so that gives us sine squared, minus the top, which is cosine, times the derivative of the bottom, and the derivative of sine is the cosine, so we have minus cosine squared, all over the bottom squared, so all over the sine squared. Well, the cosine squared minus the sine squared is 1, so if you do it the opposite way, sine squared minus cosine squared, you'll get negative 1, so we get negative 1 over sine squared. Of course, 1 over the sine is the cosecant, so we have negative cosecant squared of x. See, we haven't taken the derivative of the cosecant yet. If you're taking the derivative of the cosecant, you're really taking the derivative of 1 over the sine. And the quotient rule says you take the derivative of the top. The derivative of 1 is 0 times the bottom. Not that it matters, because 0 times any number is 0, minus the top, which is 1, times the derivative of the bottom, which is cosine x, all over the bottom squared. So we end up with negative cosine x over sine x times sine x. And 1 over the sine is the cosecant, and cosine over sine is the cotangent. Okay, so if we look at it then, the only ones that really differ from what happens in the case of the usual trig functions are that the derivative of the cosine is not the negative sine, it's just the regular sine, and the derivative of the secant is not the secant tangent, it's the negative secant tangent. The rest really fit the patterns for trigonometric functions.